Our next lesson is about arc length, radian measure, and sector area. And this goes along with Module 5, Lesson 9. And in this lesson, we're hitting one CCRSM standard that talks about arc length, radian measure, and sector area. Let's get started. We are in Lesson 9, and I first want to give you a definition, and that is the definition of a sector. Let arc AB be an arc of a circle with center O and radius R. There's a picture over here on the right. The union of all segments OP, where P is any point of arc AB, is called a sector. So this region right here is called a sector. Okay, so although you may have called a pizza slice a triangle, it's actually a sector. Or a slice of pie is a sector. Anyway, there's lots of very tasty sectors in the world, but the name of that shape is a sector. And we're going to find down here in example 2 the formula to find the area of a sector. A says circle O has a radius of 10 centimeters. What is the area of the circle? Well, here's a circle, and the radius is 10 centimeters. And I know that the area of a circle is pi r squared. So this is pi times 10 squared, or 100 pi square centimeters. What is the area of half the circle? Well, if I had half the circle, then it would be half of this, or the area would be 1/2 pi r squared, which is half of 100 pi, which is 50 pi centimeters squared. What is the area of a quarter of the circle? So here's my circle. Here's a quarter of the circle. And this area would be 1/4 pi radius squared, which is 1/4 of 100 pi, which would be 25 pi centimeters squared. D says make a conjecture about how to determine the area of a sector defined by an arc measuring 60 degrees. Well, let's think about this. If I have a circle and I have an arc of 60 degrees, or a central angle of 60 degrees, then I would want the area to be 60 out of the whole circle, which is 360, times pi radius squared. And so that would be 1/6 times 100 pi, which is 16.6 repeating pi centimeters squared. All right, so what we'll get to is down in F. It says give a general formula for the area of a sector defined by an arc, by an angle measure x degrees on a circle of radius r. Okay, but hopefully with this you can see that we are always multiplying some fraction times the area of a circle, some fraction times the area of a circle, some fraction times the area of a circle. So hopefully you can see that our general formula will be some fraction times the area of a circle. And it'll be very close to this one, where with the angle measure being where the 60 degrees is. Let me scroll down and write that. So the general formula for the area of a sector is x degrees out of 360 times the area of a circle, pi r squared. All right, let me give you one more example of that. So let's say I have a circle. I want some more space. So here's a circle right here. This is an example. And let's say the angle is this right here, which has an angle measure of 240 degrees. And the radius is, let's say, 8 inches. Then what is the area of this sector? Well, the area would be the angle measure, which this angle right here is 240 divided by 360, because that is the fraction of the entire circle that I want the area of, times the area of a circle, which is pi times radius squared. Now I'll do this in terms of pi, and I get 42.6 repeating pi inches squared. And that's how you find the area of a sector. Now let's go to the very, very top and use the same idea, the same thinking, to talk about how to find the length of an arc. In A, it asks, what is the length of an arc of degree that measures 60 degrees? So here, this arc right here is 60 degrees in a circle of radius 10 centimeters. So I want to know this, the length, not the measure, the length of this arc. Well, using the same kinds of thinking, this is going to be part of the circumference. And I know the circumference is 2 pi r. Now I want a certain part of that circumference, and the part that I want is 60 out of 360. So 60 out of the entire circle is the fraction of the circumference that I want. So if I use the radius, I know the radius is 10. And so I get, let's see here, 60 over 360 is 1/6 times 2 times 10 is 20 pi. So that simplifies to be 3.3 repeating pi centimeters. D says, give a general formula for the length of an arc Dury measure x degrees on a circle of radius r. So the general formula is arc length is equal to x degrees divided by 360, because this is the fraction of the circle we want to find, times the circumference of a circle, which is 2 pi r. And that's the general formula. Here's one quick example of that. So if I have a circle here, and let's say I want to find the arc that is 100 degrees, and the radius is, let's say, 5 inches, then I can find the length of this arc to be 100 divided by 360. That's the fraction of the circumference I want, times the circumference of the circle, which is 2 pi r, where r is 5. And this gives me 2.7 repeating pi inches is the length of that arc. Now the last idea to talk about today is in E. Is the length of an arc intercepted by an angle proportional to the radius? Okay, what that means is if I have a circle and if I keep the angle constant, let's just keep it easy at 90 degrees. Okay, and I change the radius. So now if I make the circle bigger but keep the same angle, keep it easy at 90 degrees. And let's say this is 5 and this is 10. Let's just use centimeters. The question is, would this arc length be proportional with the radius to this arc length? And because they are both lengths, the answer would be yes. Okay, that this one, this bigger one, would have an arc length twice as long as the smaller one, because they're similar to each other, and because the radius is twice as long as the smaller one's radius. Okay, now the question might be is, what is the constant of proportionality? What is that ratio between the small one and the big one? Well, I'm going to go back to our equation, and the arc length is equal to x degrees out of 360 times 2 pi r. And if you notice it, this right here, if we keep the angle, we keep x constant, we don't change the angle, then that angle divided by 360 times 2 pi will be constant. And that is the constant of proportionality. If I can rearrange this a little bit, I'll write this as x degrees times 2 pi over 360. I'm just shifting over the dividing by 360 to be under 2 pi. Okay, this, by the way, is what's called the radian measure of an angle. Meaning, if you took any angle in degrees and multiplied it by 2 pi over 360, that would give you that same angle in radians. We've talked about radians, but we don't use radians. And here is where it's first introduced about what radians are. And angles are measured in radians through Algebra 2 and pre-calculus and calculus. And as far as you go in mathematics, they use radians because it has some nice mathematical properties that degrees don't have. Okay, let me just give you a little bit of idea of what radians are. Okay, so here's a circle, and an angle of radians, of 1 radian, would be the same length as the radius. So this might be 1 radian. If I drew it so that the arc length, this arc length, was the exact same as the radius. Okay, 2 radians would be where it's twice as long. So this angle right here would be 2 radians. Okay, so if you, it's the ratio between the radius and that arc. Okay, some nice ones to know about are a semicircle. So halfway around is going to be pi radians, because that arc length is pi times the radius. And the last one I'll share with you is all the way around 360 degrees is 2 pi radians, is all the way around. Okay, again, this is just an introduction. Our standard is that you know that radian is the constant of proportionality between the radius and an arc length. All right, this video is about arc length, radian measure, and sector area. Thank you for watching.